Hi everyone, my name is Vinay, and today I'll be presenting my Master's in Cybersecurity Practicum titled Improving Evidence Collection and Data Recovery in Cloud Forensics. In this presentation, I will be briefly explaining the research gap, my proposed framework, implementation, evolution, and the key results. The motivation behind this research comes from the increasing number of cloud-based cyber incidents where volatile memory plays a crucial role in investigation, as it stores running processes, encrypted keys, active network sessions, malware artifacts, and much more. While memory acquisition tools are widely available, ensuring the integrity of memory evidence during remote transmission remains a major challenge. In the previous study by Sulin and Mark presented a remote acquisition forensics tool, a RAF system, which is designed to capture disk drives and send the collected evidence remotely over the network. However, the research is not able to detect real-time corruption or has any retransmission mechanism for corruption. Also, it is specifically designed for physical devices like removable devices and hard disks. To address these gaps, I designed and implemented a secure acquisition and verification framework. I will now explain the methodology following in this research. This research follows a four-stage methodology. The first stage is acquisition, where the live memory is captured from the system. The second stage is data transmission, where the data is transformed into chunks, then hashed and encrypted. The third stage is verification, where the data is transmitted and the hash is verified. The fourth stage is evaluation, where I'll test the performance of the model. In this research, the hardware used is the host machine running Windows 11 with 16 GBs of RAM and 16 core processors like CPUs. The main focus is on the virtual machine, where we have two virtual machines running. The first one is running Ubuntu version 22.04 with a base memory of 4 GBs and two core CPU processors. Similarly, the next machine is Windows 11 with 4 GBs of RAM and two core CPU processor. This is the workflow for the research, which will be understood easily in the implementation part. So let's move on to my screen. I will now demonstrate the practical implementation of proposed framework, starting from live memory acquisition on the Linux virtual machine. The Linux machine is running on Oracle VirtualBox. This is my Linux virtual machine, which represents the target cloud system. I am using AVML to capture the live physical memory. AVML allows acquisition without interacting with the disk, which preserves forensic soundness. To use AVML, first we need to give the sudo permission and the file name. At this stage, the full physical memory of the running process is being captured in the raw format. This memory dump contains volatile artifacts such as running processes, network activities, and encrypted keys. The memory dump has now been successfully acquired and will be used as the input for secure transmission. This is the framework scripted in Python, which, after acquisition, processes the memory file, divide it into fixed size chunk, which can be done over here. Each chunk is hashed using SHA-256 before transmission. Our host machine is working uh, as a Windows forensics workstation and a receiver. The receiver script is been encrypted over here. The receiver listens for incoming encrypted memory chunks. To run the framework, we first need Python installed in our Linux operating system. This establishes the connection in between the host and the target. The receiver listens for incoming encrypted memory chunks. The sender sends each chunk in hashed format, which, on receive, is decrypted and its hash is recomputed. The recomputed hash is compared with the sender's hash to verify the integrity in real time. As shown on the screen, the hash values are matched successfully, which confirms that the transmission data has not been tampered with during transmission. After successful verification of all chunks, the final memory is reconstructed as fully verified forensics memory dump. This image is now saved for legal and forensic analysis. This completes the live demonstration of the proposed secure memory acquisition and verified framework. Now, I'm demonstrating the same process on the Windows operating systems. The same Oracle VirtualBox is being used and Windows 11. This is my Windows 11 machine running on Oracle VirtualBox. To acquire memory on Windows, we use FTK tool imager. It is the simplest process on Windows because it uses a graphical user interface. Simply on Xtero FTK imager, we have to click on the files, capture memory. Here we have to select the destination file. For now, I'm selecting desktop. Give whatever name you wanted to give and start capturing the file. This will start capturing memory. The speed depends on the memory you have. In my case, I'm using 4 GB of memory. After capturing the memory, it will show a successful message. And a dump file will appear on the screen. Now we have the sender.py file in our Windows operating system. Similarly, in our host machine, we'll start the receiver.py. This will start the listener on our host machine. We'll start the sender. This will start transmitting the chunks from the target to the host. Each chunk is again hashed and transmitted over the network. The hash is then verified, and this process will go on until all the packets are received. After successful verification of all chunks, the final memory image is reconstructed as a fully verified image. The image is now saved for legal and forensic analysis. After implementing the framework, multiple experiments were conducted to evaluate its performance and integrity. And I will now present the key results. The framework has successfully transmitted and verified, ensuring 100% integrity, and in compare, Windows has outperformed Linux. At the end, to conclude, this research focused on improving the integrity of live memory acquisition and transmission in cloud-based forensic environment using inline verification. The proposed framework successfully ensured real-time integrity, verification of memory evidence using encryption, hashing, retransmission mechanism. It improves upon the baseline research by providing end-to-end integrity assurance in virtual cloud environment. This work demonstrates that secure live memory acquisition with inline verification is both feasible and forensically sound. Thank you for your time and attention.